Hey everybody, I'm back and today we are discussing reducibility with respect to FG modules and of course representations, because as we've seen, FG modules and representations are really talking about the same things. They're two sides of the same coin. But before we talk about reducibility, we need to talk about the notion of an FG submodule. It's actually really straightforward. Let's have a look now. Okay, FG submodules. So if you have V, which is an FG module, right? So V is a vector space over some field F. G is a group acting on that vector space in the ways that satisfy our conditions we talked about earlier. And then you have W, where W is a vector subspace of V. If W is also closed under the action of G, then it gets upgraded to an FG submodule from a vector subspace to now a submodule. What we mean by closed under the action of G is that if you take any vector in your subspace, W lives in our subspace, our subvector space, and we let G act on that as described by our FG module, right? Because little w is in big V, so we know how to act with our group element on here. If when we act on all of our guys in our subspace, we always get somebody back in our subspace, then we say it's closed, and our vector subspace gets upgraded to an FG submodule of V. So now we can get into what it means for an FG module to be reducible or irreducible. We say an FG module is irreducible if it is non-zero, it has more vectors in it than just the zero vector. It's, an interesting vector space. And it has no FG submodules except for the zero FG submodule and itself. And we'll come back to these in an example later. If it does have a non-trivial submodule, these guys are the trivial submodules, then we say it is reducible. And we'll see why that is in just a second. As always, when you're talking about FG modules and representations, we're really talking about the same thing. So we say that a representation is irreducible/reducible if the corresponding FG module, Fn, is irreducible/reducible, right? Once we let our representation act on the suitable vector space, it forms an FG module. The representation, if we think of its operation as matrix multiplication, gives us an FG module. We've talked about this before. The definitions are the same for representations and FG modules. Okay, so here's example 0. I called it 0 because it's a really cute example. It's more technical than anything. So if we have V, an FG module, then we have that the zero vector subspace and V itself are FG submodules of V. Why is that? The zero vector space is certainly going to be closed under the action of our group G, because G always maps the zero vector back to the zero vector, so any linear combination of the zero vector with itself is going to give back the zero vector. This is trivial. That is an FG submodule. And then V itself is trivially a submodule because it satisfies the conditions. We just have to say this because V is a vector subspace of itself. So it is also an FG submodule of itself, right? It satisfies those conditions. That's the definition of what an FG submodule is. So these are both FG submodules. They're both trivial. We don't care about them. Now to the first interesting example. Okay, example 1, I'm gonna revisit the group from my previous video. We've talked about this guy before. We have the group generated by the permutation 1, 2, 3. It's isomorphic to C3, the cyclic group with 3 elements. And let V be the 3-dimensional FG module defined by these guys right here. This is just a permutation module, right? We talked about this earlier. You can see that all of the actions are what you would expect, right? For example, right here, we have E3 gets mapped to E2. Why is that? Because this permutation group element sends 3 to 2. But now let's look at the vector W, which lives inside V, and it's just the sum of the 3 basis vectors. I give them little hats because they're units. Now consider the subspace W, which is the span of our vector V. Spans, by construction, define a vector subspace. So that's a subspace, check. But notice it's also an FG submodule of V, because if we look at the action of all of our group elements, in this case there's only 3, but if we look at the action on W, it always gives us back W. And this subspace is just a scaling of this one vector, right? It's a one-dimensional subspace. You can think of it as a line. So this is our basis vector for that space, and the action of our 3 group elements just give us back W. So W is inside of big W, the subspace. The only other elements in the subspace are just going to be scaled versions of W, and we can always pull out our scalar. So we know that this subspace is closed under the action of G. So this is indeed an FG submodule of V. So it is reducible. We have found a non-trivial FG submodule. Bam. Now example 2 is just continuing on with the same FG module. So we have G from before, let V be the same FG submodule, but now we're gonna consider this particular basis. What I'm doing here, what I'm thinking is I'm starting with the basis of our subspace and extending it any way that I please so that it now is a basis for our entire FG module V. So this guy right here is the basis for W, right? It's just a one-dimensional subspace, but it could be more in principle. And so if we use this basis as a map to send the action of our group elements to the space of 3 by 3 matrices, right, as we talked before, that turns our FG module into a representation, right? We have an FG module, we pick a basis, that makes it a representation, maps our group elements to matrices, and this is what we find. So notice now we have two representations for our FG module. We have the trivial representation, that's up here in this left-hand corner. It's the one-dimensional trivial representation. And then we have this new representation, which is a two-dimensional representation, which we get from this bottom right-hand corner, and that is no accident. So now if we consider the map that sends our group elements to these 2 by 2 matrices, we now have a two-dimensional representation of our group G. If we're sticking with real numbers, it turns out that this is irreducible. If we consider our FG module for F to be C, then we can reduce this further. At the end of the video, I'm going to show you a trick that my grandma taught me on how to reduce FG modules with a lot less effort. She probably learned it from her grandma, who probably learned it from her grandma. It's just one of those traditional things, and I'm really excited to share it with you guys. But before that, I have some more remarks to make, talking about reducibility and irreducibility when it comes to FG modules. So let's look at that. If V is a reducible FG module, then there exists an FG submodule W with dimension greater than 0 but less than the dimension of V. This follows from us throwing away the trivial submodules. The 0 submodule is the only submodule that is going to have dimension 0, and the other trivial submodule, being V itself, is going to have the same dimension as V. So if it is reducible, neither of those are the submodules we're talking about. So our submodule has to have a dimension greater than 0 and less than the dimension of V. And we'll come back to that in a second to prove a useful result, a really quick proof. So if you take some basis 1 of our submodule and extend it to be a basis B of our original FG module, like I did in the example earlier, then for all group elements, the matrix, where we use our basis to map our group element to a matrix, has this form, right? This is what we saw above. In the top left-hand corner, we're gonna have a matrix. Bottom right-hand corner, we're gonna have a matrix. And these guys are not necessarily square. These are always gonna be square. It turns out these are going to be representations, and this is just some fluff. So if we come back to our example here, right, we have a representation, it's going to be square, representation that's square. These are not necessarily square. That's what I mean by Y. That's what I mean by the zeros. The book is going to have the 0 and the Y's swapped, because in the book, they are always talking about group elements acting from the right, but we're sane human beings, so this is acting from the left. So this is switched if you are following along with the text. That is important to note. And we always have that this representation up here is going to be a K by K matrix where K is the dimension of our subspace. And that's going to follow from the fact that we extend our basis starting with the basis for our subspace. So that's where this representation comes from. And then our extension is going to tell us what Z is. So these two guys are square, Y is not necessarily square. Notice that these guys are again representations. You can think about it if you multiply this guy with, say, X of H, Y of H, Z of H, you're going to have X of G times X of H, Z of G times Z of H, a bunch of fluff up here, a bunch of zeros over here, and those are going to give us two new representations. Now for that nifty result. So if your FG module V has dimension 1, we know V is irreducible. Why is that? Because if we come back here, we know that the dimension of a submodule has to be greater than 0, but less than the dimension of our FG module. So if this is 1, this is 0, the dimension of vector spaces has to be whole numbers. There does not exist a number between 0 and 1. So we know that one-dimensional FG modules are irreducible. That's good to know. You didn't think I forgot about that trick from my grandma, did you? Here, okay, follow me into the kitchen. Okay, how am I gonna do this? I've never filmed here before. Okay, so I don't know if anyone's heard of this nifty trick before, but if we start with our FG module, here we just have V, right? It's a span of 3 vectors. You know, if we look a little closer, we can see this is the FG module we were talking about before, right? We have our cyclic group of order 3. So what we want to do is we don't want to put the heat on too high. For reducing, the trick is to go low and slow. Just like when you're learning how to climb trees. So we're only going to put this on to maybe 3, like low to medium heat. And we're just going to rip this up. You want to get your textbook in there first, just for flavor. Cutting it up a little, spreading it around, that just helps it reduce a little faster. I'm going to throw in a little bit of physics for flavor. Okay, just 1 page. You don't want to overdo it. You don't want to overspice it. You can just crumple that up. Throw that right in. Leave it low and slow. One more time, low and slow. Okay? We can see now it's 2:53. 20 minutes should be plenty. Okay, so you can see now it's 3:15. I let it simmer a little bit longer just to really help it reduce. Low and slow, right guys? Okay, so you can go ahead and turn that off before we burn anything, and take that cloth off. All right, if we did this right, what we have here is some nice reduced subspaces. Look at that. Okay, so these can be really hot, so make sure you use some utensils. Make sure you're not burning your hands. I just grabbed a couple of forks, and if we look, I'm pretty sure when we pull this open, it's kind of hard to see, but that right there, look at that. That right there, that's our first one-dimensional subspace, our FG module, right? All the details there. Woo-hoo. Just like Grandma used to make. And there's W2, our 2-dimensional submodule. Oh my God, oh, this worked great. Oh. Okay, all right guys, that's it for today's video. I hope you like my grandma's trick. I will see you guys next time. Thanks so much for waiting for my videos. I hope you enjoyed this video on reducibility, and I will see you next time for, I think, group algebras.